last lecture of this year's series of Science for the Public. We're going to do things a little bit differently tonight than the way we've done before. We've decided at the beginning of the planning for this series of lectures, to have local teachers involved in introduction of the speaker. And here at the last one, we finally got around to it. So the person who's going to be doing the introduction of our speaker today is Anne-Marie Montgomery, who has been a teacher and administrator here in Riverside for about 20 years. She is currently the Instruction Services Specialist, whatever that is, for Secondary Mathematics and Instructional Technology at RUSD. She's also the co-principal investigator for the California Math Science Partnership and supervisor of teacher education for the Math Science Integrated Cohort at UC Riverside's Graduate School of Education. She's a 2-degree alumna from UCR. Both her parents are UCR alumni, as are her sister and her husband. In 1994, she was named Riverside County Math Teacher of the Year. Please help me welcome Anne-Marie Montgomery.
I'm still trying to figure out what an instructional services specialist says myself. Good evening. Forgive me for reading some notes. It's my delight and honor to introduce Dr. Jeanie tonight. I had the pleasure of meeting her last week and also did a little research of my own. Today she'll give you a talk. I'm not going to read you the title. Like you, I'm eager to learn more about graphene and nanotubes, and I wonder how these materials are already affecting scientific research and industry. Quoting directly from her faculty webpage, her research explores novel physics and phenomena of nanoscale systems, such as nanowires, carbon nanotubes, and organic molecules. I also read a UC newsroom press release last week, which leads me to believe that we here in Riverside, California, are witness to the next wave to revolutionize electronics. And Dr. Lau and her students are at the epicenter of this innovation and discovery, right here in Riverside. She's an associate professor of physics in the Physics and Astronomy Department at the College of Natural and Agricultural Sciences at UCR. As a young woman, came from Hong Kong to study at the University of Chicago, went on to Harvard to earn her master's and PhD, did a research associate at Hewlett-Packard, and came to UCR in 2004. We were very lucky to have her. Her awards and honors are numerous, including a Richter Fellowship for Undergraduate Research, a David W. Granger Senior Scholarship, a National Science Foundation Career Award, and a Robert T. Poe Faculty Development Grant. She's published many research articles in peer-reviewed journals. Of special note, she received national recognition that only a few outstanding researchers are given at the beginning of their careers, the Presidential Early Career Award for Scientists and Engineers. And because of that, she got to go to the White House and meet President Obama. Yeah. These awards are based on innovative research, the frontiers of science and technology, as well as community service as demonstrated on scientific leadership, education, and community outreach. And she exemplifies that at UCR. She actively involves high school, undergraduate, and graduate students in her research. She's a founding faculty member of the UCR Undergraduate Research Journal and organized the Women in Physics lunch group for students, postdocs, and faculty. When I was talking with her last week, a few things became clear. She's warm and friendly, she has a terrific sense of humor, and she's very inspirational. She has an intense curiosity about her field, devotes her time and energy, probably loses the sleep over it, to developing and unraveling the mystery, finding new solutions to the problems. She's present at the moments of never-before-witnessed discoveries in an essentially invisible world, which is quite a rush, according to her, and is able to take these incredibly complicated concepts that are changing our world and explain them to us in a way that we can understand. Please welcome me. Welcome. Join me. Welcome me. Dr. Jeanie.
Well, thanks, Anne-Marie, for this kind introduction. I can barely recognize myself at the introduction. It's an honor for me to be here to tell you about my field of research. Okay, now if I can get this. Okay, which is graphene, so we have this title, Size Matters, Nanotechnology in the Carbon Flatland. Okay, now if this nanotechnology works, apparently not. Okay. All right, so here, this is a brief outline of the talk. I will start with introduction to nanotechnology, the past and the present status of nanotechnology. And the last 40 minutes of the talk, I'll talk about graphene. What is graphene? Why it is interesting, and how it can impact our lives in the present and in the future. And then conclude with a brief conclusion. Okay, so nanotechnology 101. All you want to know about nanotechnology, but it's free to ask. Okay, what is nanotechnology? So definition just from the government nanotechnology website: creation, control, and manipulation of matter on a scale 1 to 100 nanometers. Okay, so next question is, how big is a nanometer? So 1 nanometer is 1 billionth of a meter, 100,000th of the width of a human hair. So maybe you want to say, okay, I still don't, it sounds small, but I still don't know how small it is. Okay, so now here this analogy. If you take a basketball and blow it up to the size of a planet, and the nanoscale basketball, which is so-called the buckyball, which is basically contains of 60 carbon atoms, about 1 nanometer in diameter, will become the size of a tennis ball. So this is how small 1 nanometer is. Okay, so here is a chart of the scale of small things. So let's take something which probably a smaller thing you can see by naked human eye. That is basically the width of a human hair. So that's about 100,000 nanometers in diameter. And you can go down the scales. For example, how many of you have seen the spider silk talk in the past 2 weeks? Yeah. So the spider silk is actually pretty big by our standard. They are about 20,000 to 2,000 nanometers in diameter. The blood cells, human blood cells, about 1,000 nanometers in diameter. Bacteria, roughly 200 nanometers. And then we can go down to virus, roughly about 30 to 50 nanometers in diameter. So size of the virus is about 30 or 50 nanometers in diameter. Then we can go down to the size of human DNA. Double-stranded DNA is about 2 nanometers in width. So this is what we're talking about, so very, very small things. And then, okay, you can go to sub-nanometer length scale. When you, say, have a solid-like metal, the interatomic spacing is about 1/3 of a nanometer. So we are really talking about in a molecular and atomic scale. So that's what nanometer is. And the atom itself, depending on what atoms you talk about, there's some bigger, some smaller, but most of them are about a few percent of 1 nanometer in scale. You can even go down further. For example, go to high energy physics, particle physics. The protons about 1 millionth of a nanometer. But yeah, so yes, that's the realm of my colleagues in nuclear physics or particle physics. But for things that you can actually make and use and stable, when in everyday life, so molecules and atoms are probably what you're going to get, at least for the foreseeable future. That's why nanotechnology is very relevant. Okay, so that's nanotechnology 101. And you might want to ask the next question, which is also hardest to answer. Okay, why should I care? Okay, my answer is, do you have all day or all night? But this is hopefully what I want to convince you of by this lecture. This is a huge topic. I cannot possibly cover everything, even the field of graphene itself, with new daily breakthroughs, well, at least weekly breakthroughs, it's impossible to cover in this lecture. So I just hope to give you a little bit of flavor. If you have any questions, please just ask me after the lecture or email me. Okay, so where does nanotechnology begin? Different people may have different accounts, but many people agree that it begins with this visionary speech given by Richard Feynman, who is Nobel laureate and professor at Caltech. So he gave a speech at American Physical Society meeting at the end of 1959. The speech is titled, "There's Plenty of Room at the Bottom, an Invitation to Enter a New Field of Physics." So this is very, very visionary speech. I just want to read a few passages from there. He says, "I would like to describe a field in which little has been done, but a tremendous amount can be done in principle. This field will tell us about strange phenomena in the complex situations and have enormous number of practical applications." So this field is how to manipulate things on a small scale, that is miniaturization. And so he proceeded to predict how, with enough miniaturization, you can write all the information accumulated by mankind in this world in a small cube that's barely the size of a piece of dust. So that is amazing. This is what his vision. And so he made a few predictions. For example, computers back in the 1950s filled a room. He said, why can't we make them very small? Why can't we make the wires about 10 to 100 atoms in diameter? Why can't if you can make computers much more complicated, then they can render judgments? So all of these predictions have come true, right? So that was the beginning of the nanotechnology, and in the past 50 years, we've made tremendous progress. And this progress is usually encapsulated by the so-called Moore's law, which is first observed and predicted by Gordon Moore, co-founder of Intel. So he said the number of transistors on an integrated circuit doubles every 18 to 24 months. And so this is the chart just showing the number of transistors on a circuit starting from 1970. So for 1970, you can put about maybe 4,000 transistors on a chip. A transistor is this elementary computing element that at the heart of every computer. So it's one basic element of a computer. So the more element you can put in there, the more complicated tasks the computer can perform. So starting at 1970 started from 4,000, so it doubles every 18 to 24 months. And so by 2007, we can put 1 billion transistors on a chip, which is a size this big. Okay, so whoops, by 2010 or 2011, it's going to reach 10 billion transistors on a size this chip. So imagine that's more than the number of people on this planet from something this big. It's amazing progress over the past 50 years. So there's another way of looking at the Moore's law, which is the feature size, the size of transistor as a function of number of years. This size of transistor it will be reduced by 30% every 18 to 24 months. So the size will be reduced by half every 3 to 4 years. And so you can see it's so starting from 10,000 nanometers in 1970s. Now, in 2001, Intel just came up with 22 nanometer feature size chips. So let's just look at this in the scale of things. So we have naturally occurring small things I already went through. And this part is Intel chips. For example, 1980s Intel chip, the feature size of one of those transistors is roughly on the order of a spider silk. By 2000, the feature size of transistor is on the order of a bacteria. So each transistor is about, well, I would say the little wires that make up the transistor is about the size of a bacteria. And now in 2010, the feature size is that of a virus. So you can see how far we have gone down. So there's so much room to go for from feature size up to the top and gone to we are already reaching the size of a virus for each transistor. Okay, so that's another way of looking at this, how much progress we have made. This is one of the first electronic calculators built by IBM Harvard Consortium. They call it Automatic Sequence Control Calculator. It's actually still on display at Science Center at Harvard. You can actually just go in and see it. So it fills a room. It weighs 10,000 pounds. It performs 9-digit calculation in 6 seconds. And it costs $30,000, which is $500,000 in today's money. And of course, everyone now knows that we have this, right? The iPhone, which you can fit into one of those guys' pocket, which is of course very small, very light, very fast. It's a camera, it's an iPhone, you can browse the internet, you can play music, it tells you where you are on this planet, everywhere you can calculate, you can play games, you can keep calendars, everything, right? So this is something probably not even Feynman would dream of back in those days. And it only costs $300. Well, I shouldn't say only, but compared to $500,000, that's a very small number. Okay, so let's see we can see that most of Feynman's prediction has come true. And so he predicted a computer will be much smaller. Yes, it's very much smaller and actually much faster too. And he predicted the wires can be made about 100 atoms in diameter. And right now, the feature size is 22 nanometers, so that's roughly 60 to 17 atoms across. And at the time, we can only do simple calculations. He predicted the computer can run the judgment. Of course, we know Watson. Everyone knows about Watson. So yes, they can actually defeat a human, the longtime champion Ken Jennings at this Jeopardy game. Very impressive. Okay, so obviously Moore's law has gave us great progress over the past 50 years, and like all good things, we don't want it to end. We want to continue this miniaturization of the electronics. So I'm just going to stretch this, extend this both vertical axis and horizontal axis. And now we can see that, so we are going to talk about the nanometer length scale. And so we can see that in the roughly 30 years, the transistor size will comparable to atoms and molecules. And okay, so why is that a problem? Actually, it's a huge problem. So there's something so-called charge leakage. For example, it's because when you get things so small, it's very difficult to tell the electron where to go. The electron has a mind of its own once it's so small. There's some things called quantum tunneling, which we should talk a little bit about, will come into play. And the heat removal becomes a huge problem. When you cram 10 billion transistors on size this small, each of them requires a little bit of power to at least operate it, then this 10 billion little power becomes a lot of power, and you can literally get burns on your laptop, right? So when you try to increase that by even more, it's important to find a way to get the heat out. And so that's a huge problem. And another problem is that when you make things smaller and smaller, so they are like little fuses, and so passing a current very easily blow it up and give you open circuit and cause failure in your device. Another problem is when you try to make things on the atomic scale, even a little bit of imperfection can cause a device failure. And so finally, there's this challenge is that there's going to be a lot of unexpected phenomena simply arising from the fact you are confining electrons and atoms to a small length scale, and there's a lot of quantum mechanical effects, and this is actually both a challenge and an opportunity. A challenge because we need to understand their behavior to guide rational design of the devices. Opportunity is because if we understand and can control this new phenomena, then we can use them to impart new functionality to the device, and we can make new classes, novel devices, which perhaps has not been possible before. Just to summarize, so we want to continue this Moore's law. We want to understand how electrons and atoms move in the nanometer scale, and we probably also going to need new material other than silicon. Silicon right now is the material of choice in the electronic industry. That's what we have used for the past 50 years. Okay, so what are we going to do? So let me just look at a little bit of history. Actually, the first transistor was made out of germanium in 1947, developed by the Bell Labs. And but soon you will find out a few years later, the researchers find that silicon is actually much better, and that's what our electronic technology is based for the past 50 years. So maybe we'll just go up the periodic table, and perhaps we'll just go use carbon. Okay, so why carbon? Carbon is actually the most chemically versatile element. So it consists of 6 protons and 6 neutrons at the center of the nucleus, and it has 6 electrons, with 2 electrons in the inner shell or inner orbit, and 4 electrons in the outer shell. So these 4 electrons are so-called valence electrons, are responsible to forming all the chemical bond. So these 4 electrons, for example, there are many ways to arrange these 4 electrons. For example, the 2 carbon atoms can share 1 pair of electrons, and it's so-called single bond. They can share 2 pairs of electrons, the so-called double bond. They can also share 3 pairs of electrons, so-called triple bond. And so this chemical versatility of carbon is actually is responsible for formation of the fact that carbon can form compounds with most elements in the periodic table, and that's why it's also carbon is also basis of life. We are all made of carbon and hydrogen, mostly. Okay, so now so let's look at this scale chart again. So we are at the size of virus. So when we go down some more, we are reaching the size of atoms and molecules. And so I'm just going to talk about graphene mainly with just a touch on carbon nanotubes. These are actually basically giant molecules. They are micromolecules, and they are a single atomic layer thick. And they are very, very small, and they have a lot of fantastic properties. So that that's why they emerge as one of the most promising, I should say probably the most promising candidate to replace silicon. Okay, so let me just talk about carbon flatland, which is graphene. So graphene is a single layer graphite. The atoms are arranged in the honeycomb lattice with so a bunch of hexagons fill the plane. Each carbon atom is covalent bonded to 3 neighbors, and then they can donate the 1 extra electrons, which can roam freely on the sheet, and that's why graphite is a good electrical conductor. And the graphite layers are held together by weak van der Waals forces. So okay, so here we have some graphene sheet. Okay, but I'll pass it around in a moment. I need to do it a little bit demo later. Okay, so so carbon is actually has been dubbed as a mother of carbon allotropes. Graphene is so it's a 2-dimensional material because it forms this plane, and if you stack it up, you can form 3-dimensional graphite. If you roll it up, you can actually form the 1-dimensional nanotubes. And depending on how you roll it up, so for example, you can roll up this way, or you can roll it up at an angle, like that. Okay, so you will have carbon nanotubes. And carbon nanotubes, so depending on how you roll it, you can have metallic or semiconducting kind of carbon nanotubes. And these are discovered in 1991, and there's a lot of also technological promise for nanotubes. For example, a more dramatic one is, for example, to make the cable for a space elevator. And if you make a nanotube, and if you cut out the right part from the piece of graphene and roll it up, you're going to have a C60, or so-called buckyballs. And so these are 60 carbon atoms, and it was discovered in '85, and the discoverers was awarded the Nobel Prize in Chemistry in '96. Okay, so now you can see that carbon is really so graphene is like the mother of carbon allotropes, and you can get all of this C60 nanotubes and graphite from graphene. And ironically, graphene was the last to be discovered. So all of these has been discovered prior to graphene. Okay, so maybe I'll just pass some of this around. You can take a look. And so these are nanotubes. Some semiconducting, and some of them are metallic. See if you can tell which one. This is so-called Carol tube. Okay, so here's a brief history of graphene. It was actually graphite mine was first discovered in 1550s and was used to mark sheep. That's the first use. And in the 1800s, modern-day pencil was developed by combining graphite with clay and put it in a wood casing. And in by 1900s, graphite found a lot of industrial use, for example, in crucibles, electrodes, lubricants. And in 1947, the theory of electron movement in graphene was developed, and this was still used a lot today. And so in the 1960s and 90s, actually monolayer graphite, that's what they called them at the time, it's actually graphene, was found on metal surfaces at high vacuum. Except the researchers find that think they are very, very annoying because that's what they wanted to study metal surfaces, very clean metal surfaces, but they find that there's always a little bit residual carbon atoms which spontaneously form on the surface of carbon atoms. Very annoying. So they try their best to get rid of it. So there's a resurgence in graphene in the late 1990s. So there's an attempt to make graphene by very fancy techniques using, for example, equipment costing hundreds of thousands of dollars. And so in 2004, Klein and Novoselov from Manchester University, UK, they isolated graphene using Scotch tape, which is very cheap, as we know. And 2005, this Manchester group and also Philippines group in Colombia, they showed that electrons in graphene are massless. And with that, I should say the rest is history. So there is a huge bandwagon effect. Everyone. All the physicists, chemists, material scientists, engineers, industrial researchers, academic researchers, all converging through me on graphene. I always feel like let me on. I want to be on the bandwagon too. Right, so it's a huge increase. This is the physics papers basically published with keyboard graphene. You can see increases very dramatically since the discovery of graphene. This is late 2004, and so it's reaching about 1,000 papers per year, and that's all physicists. If you count all the other chemists, material scientists, engineers, you need to multiply this by a factor of 4 or 5. So lots of people are studying graphene. So it's a very interesting field. Okay, so why is it? Oh, I should say that. So of course, these two guys, Andrew Gam and Kostya Novoselov, was awarded a Nobel Prize for their groundbreaking experiment on graphene. Yeah, so that was last year. Okay, so what is the Nobel-winning experiment? The beauty of this thing is that everyone is doing. Oh, you can do it, and every school kid is doing it. Is that you can just do it with so-called mechanical exfoliation. Of course, that's just jargon for pencil writing or rubbing. And and another important discovery is that you can actually see it by eye, well, under optical microscope. This is actually a single layer graphene right here, and about 2 layer, 3 layer, and this is a thicker, which is probably 5 or 6 layer graphene. So this is amazing. You think it's single atomic layer thick. You can see it with your eye. Right? So that's actually quite a surprise to a lot of people. And here is the largest graphene today we obtained by rubbing. My student obtained by rubbing. And this is about 1 millimeter in size. And this is a piece of my student's hair on the same scale, just showing how big the piece is. And with this, I want to introduce my undergraduate student, David Tran. He's going to give us a live demo of how to do this Nobel-winning experiment right here.
Should I set on?
Yeah.
Okay. Or Can everybody hear me okay? Yes. Okay, so as we've shown earlier in the slideshow, graphite is something that's created by a bunch of carbon atoms coming together, and it occurs naturally in nature. and we need to liberate the graphene from inside the graphite. And the tool we use is Scotch tape. This is Nobel Prize winning stuff. So first thing we need is Scotch tape. The second thing we need is carbon atoms coming together naturally in nature, which sometimes is diamonds. In this case, it's graphite. And
I should say you can buy graphite free from a just call up some natural graphite supply company. You say one sample, they'll just send you something this big. Okay, so it's free pretty much.
Carbon is everywhere, so it's not very hard to acquire. And the next thing we need is silicone wafer chips, which we will eventually put the graphene on top of when we're creating our devices. So first, we take a strip of Scotch tape, and then we fold over the ends so that, okay, okay. Yes, Scotch tape is very statically attractive, so sometimes it's hard to work with. Next, we take a piece of graphite. These are very small pieces of graphite, so I don't know if any of you can see this. Yeah, just take my word for it. There is graphite on these tweezers. And then we deposit the graphite onto the piece of Scotch tape. And there you have it. A piece of graphite on Scotch tape. So why are we doing this? Well, graphite is a large clump of many individual carbon bonds.
Yes, layers.
So when we fold the Scotch tape over onto itself, with the graphite in the middle, and we unfold it, it cleaves the piece of graphite into two individual pieces. And again, you probably can't see this, but believe me, there are two individual pieces of graphite. So we repeat this process multiple times. And eventually, instead of a few individual pieces of graphite, you end up with a very fine dust of gray. And then after you have it broken up into a lot of individual pieces, you take the silicone chip and put it onto the Scotch tape, onto a spot that now has graphite on it. So the chip is placed onto the tape. Hopefully you can see this a little bit better. It's like a centimeter wide. Those of you that aren't nearsighted. And put it on the table, and you rub gently on the Scotch tape so that the graphite comes off onto the silicone. And if you rub not hard enough, nothing comes off. If you rub too hard, the Scotch tape does its job and gives you a nice layer of adhesive that you can't work with. So this is harder than it looks. Okay, now we have our silicone piece with graphite deposited on it.
So I guess we have to connect.
Let's change the projector to see what's under the microscope. Okay. Turn on the microscope.
Well, that's graphite for you.
Okay. Let me get this.
Well, you are not getting it.
Okay, that's a little bit too high.
Okay. Well, you have to.
Yeah. So here we have a piece of
All right. Well.
silicone. Wait.
Oh.
Okay. So now.
Oops.
Whoops,
Nothing.
A little bit right. So I'll just turn it down. A little bit too far down.
I think you need to adjust the contrast.
This is very tricky. Okay, there we go.
And this is just probably.
Yes.
What are they?
This is what you end up with. You have the silicone chip with graphite all over it. So you might be wondering, where's the graphene? This is where you bring in the undergraduates who will look through the graphite and look for the graphene.
That's why I need lots of undergrads in my lab. Or high school students. Any high school student want to work on Nobel-winning experiment? Contact me.
Okay. So now now that I've got a piece of graphene in my sights, let me just focus on this. Microscope is a little bit tricky to use.
Yes. Oh. Okay.
Okay.
Like this?
Move.
No, maybe I need to get to my. I need to get to my lecture probably.
Okay.
Are you fine with it?
Yes.
Okay.
Every time I zoom.
Okay.
Okay.
50 seconds. 30 seconds.
Right. So.
Oh.
There we go.
Where's the graph? Huh, I don't see anything.
This is a very sensitive stage, so sometimes it moves itself. And we've lost the image. Okay.
Well, okay. Well, maybe
sorry about that.
Maybe I should get back with my lecture. But if you want to stay around after the lecture, we'll show you what graphite looks like in real life. Okay.
Should I take this off?
Yeah.
I can keep.
Okay. Hey, back to this. Does this my now? Oh well, now it's. Okay, whoops. Whoops. What is this? All right, let me put this back on. Okay, so why this interest, right? You'll say, okay, big deal. Anyone can do it. Anyone actually have been writing with a piece of pencil actually is producing graphene on paper. You just don't know it. Okay, so what's the big deal? The big deal is that physicists have been trying to study two-dimensional systems, so-called two-dimensional electron gas, for a long time, actually for the past 30, 40 years. And they have to make this kind of system on semiconductors using very expensive equipment, for example, so-called molecular beam advertising. Actually, we have an expert in the room. And that costs about roughly $1 million. And if I want to do anything with this, crystal will grow out of that, you need to use scanning electron microscope, which costs roughly $500,000 to $1 million. And graphene is actually the democratic material because you only need Scotch tape, costs $249, and a optical microscope, which is a little bit more expensive, about $3,000. Okay, but you can see that you can really do a lot with a very modest research budget. So that's why, apart from the fact graphene has all the fantastic properties, which hopefully I'll have time to tell you about, and graphene is also a democratic material in that almost anyone with a Scotch tape optical microscope can start doing something with this material. Okay, well, ironically, it's also, even though it's very cheap to produce, it's also most expensive material ever if you want to buy it. So this slide was made back in 2008. So you can buy the graphene industries, and so they rub it on the chip, and you can buy it with a price of £1. This is a British company per micron square. 1 micron is 1,000 nanometer, and so you can do a quick calculation. Then you can see that graphene cost per gram is $1 quadrillion, okay, which is 1,000 trillion dollars. And okay, so the cost of bailout back in 2008 was also only $700 billion. Even U.S. national debt is only about $10 trillion. You know, so if only we can make treatment in graphene, we can solve all our economic problems. Okay, of course the graphene price has plummeted since then, back into from 2008. I'll tell you why, because large area graphene growth has been realized. But back in then, my lab is one of the richest labs in this country, because this single chip costs $1 million. Any one of you want to buy it from us, please let me know. Okay, so all right, so we have this huge bandwagon, everyone trying to get on. It's evolving into both. It has graphene transistor, have both fantastic properties, have lots of interesting phenomena for scientific studies, and also have technological applications. So let me just tell you a little bit about those. I'll start with the science, because I'm a scientist. I'm interested in fundamental properties of matter, and then I'll gradually go through the technology application in the little time that I have. Okay, so the first thing people do is build a graphene transistor. Oh, I don't know how to say. So here's a piece of graphene on a substrate. What you do is put the electrodes on them, and apply voltage to it. So we call one of the electrodes a source. It's like, where you use that to inject electrons. The other electrode is called a drain. We use that to drain electrons. And there's also usually a third terminal, so-called the gate, which is basically a piece of silicon underneath the graphene. And this is the gate, just like the name suggests, it's like the gate controlling a horse in a horse race. You can close it, open it. This controls the total number of electrons on graphene. And this is, I should say, this is FET, means field effect transistor. So the very first thing the Manchester group showed is that graphene behaves as a transistor. That is the most common element in the modern day computer technology. So you can see the conductivity increases basically linearly with gate voltage, that is number of electrons. And so on the one side, you basically have electron doped. You have surpassed electrons in graphene, the so-called N-type. And on the other side, you have insufficient electrons, the so-called toe-doped P-type of graphene. Basically, you don't have enough electrons. And in the middle, it's like the half glass, half empty or half full. And this is the so-called charge neutrality point, because graphene perfectly charge balanced. And also graphene can carry very, very high current density, which is this micrometer, microamp per atomic row. So I don't know how much you have know about the 1 amp, but this is actually a huge number. This is carries a current much better, for example, 20 or 30 times better than copper. And so graphene is actually, and this, if you just look at this curve, graphene is 20 times more conductive than silicon. Okay, so why is graphene physicists' favorite toy, including myself? So it is a two-dimensional flatland. It is only single atomic layer thick. And another very interesting thing that immediately captivated the physics community is that electrons lose its mass in this carbon sheet. So what does it mean? It's obviously a puzzling phenomenon. You know it's a puzzling phenomenon when it gets to the sitcom. Any of you seen the Big Bang Theory? Yeah. So so this is basically a sitcom about physicists, if you believe it. And so let me just show a clip, a couple of clips. Let's see, which one?
Electrons move through graphene, acted as a kind of mass. you been stuck?
Intellectually about 30 hours, emotionally about 29 years.
Interior angle of X is about 420 degrees.
Have you tried rebooting it? No, I think it's a firmware problem.
Hey, it's Disco.
Okay, so another clip. Whoops. Where is it? Where's my mouse? Okay.
For you.
Oh, we're killing it. Hey, Shirley.
Lord, you're ruining everything.
Okay. You can see graphene in the background.
Do I look okay?
Oh, I'm proud too.
You've been falling all night. You're used to it.
What is Shirley doing? They've been on it for 3 days, trying to figure out why electrons behave as if they have no mass when traveling through a graphene sheet.
With Marvel?
I needed something bigger than bees, now didn't I?
Sheldon, when was the last time you got any sleep?
I don't know, 2, 3 days, not important. I don't need sleep. I need answers. I need to determine where in this swamp of unbalanced formulas squatters the toad truth.
Okay, so you can see it's a very puzzling problem. Actually, not really. Actually, any beginning graduate student can tell you why. But okay, so let me just tell you briefly explain what does mean by electron lucid mass. So we know that Einstein's theory of relativity. This you probably everyone know about this very famous formula, E equal to mc squared. Little does he know that he has to make it several times to get it right. Okay, but so and actually this is only half of the formula. So this formula applies when the object is at rest. When something is moving, then you have to add the other half, which is involves momentum, which is basically mass times the speed, and the c, which is speed of light. So if you have, so this is for something. This is a whole formula for something that is moving. But for massless particle, m is 0, so you get rid of this term, then you get this formula E. The energy of a particle for massless particle. Am I on? Okay. Is simply the momentum, which is mass times the speed, times the speed of light. Okay, so when the particles, so this is what you do when the particles, you can have 0 mass, but it moves at speed of light, or you can actually have some mass, but it moves so fast that its speed is approaching the speed of light. In either case, its energy is going to be in strict proportional to its momentum. Then in both cases, we call this particle relativistic particles. So electrons in graphene are actually massless relativistic particles. Okay, so what? And so this is you can actually any beginning graduate student can tell you how to do this calculation. You can just calculate energy as function of momentum for the graphene, this hexagonal structure. You will actually have this cone shape, looks like hourglass shape, and you can see the outlines linear. That is, energy is proportional to momentum, and that's why electrons in graphene are massless relativistic particles with the speed that is 1 over 300 of speed of light. So it's a little bit slow, but still it's relativistic, which is cool, right? And you have in reality, you want to use relativistic particles, you go to the huge collider, which is mile big, and you accelerate particles so that reach really high speed. But you graphene, Scotch tape and graphite, you get the same physics. So another cheap experiment, right? So there's a lot of funny consequences because of the masslessness of the electrons. So one of those, so I'm just go through one of them, what's so-called Klein tunneling. Okay, so let me tell you a little bit what's tunneling. Okay, so if I want to walk into a wall, okay, everyone walks into a wall, you probably just be bounced back with a bruise on your forehead. Okay, but if you are a quantum mechanical particle that is very small, such as for example, electron. If you can sit at the wall for long enough, you can actually go through, except you are going to, when you go through, you have a little bit shorter, a little bit fainter. Okay. And if the wall is really big, really tall, really wide, you can still go through. but you actually go much shorter and much smaller. If the wall is infinite, really, really tall, then there's no chance of going through. Okay, so these are just non-relativistic quantum mechanics. Okay, so what if now if you have relativistic mechanics? So this is very weird, is that you can actually have a perfect chance to go through, provided the wall is tall enough or wide enough. So this is so-called Klein tunneling, named after the Swedish physicist Klein. And so this is, so just in short, Klein tunneling describes that relativistic particle pass through a barrier perfectly, provided that the barrier is high enough or tall enough or wide enough. So, tall enough. So this is very strange, but it was understood. But because the barrier required is very, very high, it's thought to be realizable at edge of black hole, so it was never observed in high energy physics. But so electrons in graphene and electrons, because of this masslessness, its relativistic nature, you can just go through. And so we have a tabletop experiment. This actually had been verified a couple of years ago. A tabletop experiment of this very high energy physics. So you just next time you write with a piece of pencil, you think you are creating black holes for the electrons. Okay, so so another thing, this is my work. I'm just going to have to tell you a little bit about electronic interference in graphene. So this is about actually 30 megabytes of data. What we do is plot the conductance as a function of gate voltage, which controls the charge density, and the voltage bias we apply between source and drain. So it may be a little technical, but you can just see the beautiful colors, right? And the very nice checkerboard pattern, very striking checkerboard pattern. It means the conductance is periodic, goes up and down as you change, for example, the number of electrons on graphene. And this is a simple example. Is that electrons are actually also waves in graphene when they are reflected back and forth between the electrodes and interfere with each other. So they do is from standing waves, and those patterns result from the standing wave formation. And again, this is something that very interesting, as you can see from this clip.
I'm sorry you had to wait. We are
Okay, so
what's this?
Sheldon's a girl.
let me just say that the background for those who didn't know. So Sheldon was stuck many days trying to figure out why electron lost its mass, and he decided to took up some manual labor so that he can flex his subconscious to work on it, and he decided to go just volunteer at a restaurant that this actress Penny works in.
I'm
Oops.
sorry you had to wait. We are swamped. What's this?
Sheldon's a girl order.
Sheldon doesn't work here.
Well, honey, not to complain, but we were starting to think you didn't either.
Is that really necessary? Good Lord. The interference pattern in the fracture. The motion of the waves of the molecular structure. I've been looking at it all wrong. I can't consider the electrons as particles. They move through the graphene as a wave.
Wave.
It's a wave! The moment to applaud would be now. Chocolate ice.
Okay, so now back to my work. I'm happy to report that I did not have to work in the restaurant to realize they are waves. Actually, I would say any undergraduate student will realize that too. Okay, so what we have shown is that basically the electrons in graphene are like billiard boards, and the graphene itself are just like a billiard table. So they can swim around, and when they collide with the boundary of the billiard table, since they are also waves, they interfere with each other. And so this is like interference wave pattern. You can see they form this kind of periodic peaks and troughs when you have two waves interfering, and this so-called, therefore we realize the form of so-called quantum billiard. It's like billiard except it's quantum mechanics with the interference effect. Okay, so why is that interesting? It's interesting for, I've satisfied my curiosity. So technologically, it's a little bit far out, but it's not inconceivable. Is that we can make electron optics. Is that we exploit the wave-like nature of electrons in graphene, so we can control the movement of electron-like optics. For example, you can try to focus them. You can make them go in certain ways. And so this is our fiber-parallel resonant cavity. This is optics. An analog, and this another thing. This work from Philippine School in Columbia is that PN junctions, for example, they can form the basis of so-called vice-LIGO lensing, which I'm not going to go into. It's just some sort of lensing effect. You can potentially focus electrons. For example, they come in parallel and then focus them to a point, or vice versa. Okay, so that's the electronic properties. Graphene also have a lot of interesting mechanical properties. For example, since it's single atomic layer, you can actually resonate it. You can make the world's smallest drum. You can make the world's smallest balloon too, because they act as impermeable membrane. And they also have some strange mechanical properties. It's actually very, very strong, very, very tough. Because of the carbon-carbon bond is very strong, so it actually takes a lot of force to break them. So it's about 200 times that of steel. It's also very elastic. So can you imagine something that's stronger than steel but so elastic? It's because it can actually be stretched by 25% and return to its original shape. So just to compare, most materials actually fail, will have developed cracks, for example, by the time they're stretched by a fraction of a percent. But yet it's also very soft. What does it mean is that because it's a single atomic layer, it actually bends very easily, bends and also buckles very easily. And here is some of our work. We show that graphene that actually spontaneously form ripples. One way to kind of just rub them across a trench. Here we can, this is a scanning electron micrograph showing the ripple formation in graphene. And we can use atomic force microscope. Basically, we just measure follow the height of the ripples. You can see they're very periodic. So this is actually easy to understand. This is basically because this graphene is strained. So here's another demo. All you need to know about graphene is so cheap. This is a piece of Saran wrap. You basically when you stretch, stretch a Saran wrap, you will actually have ripples like this. Okay, this is just from straining a very, very thin membrane. But actually, the physics of it was only understood 2003, the so-called geometry and physics of wrinkling. It's actually a very nice paper showing how you can actually understand how wrinkle forms on the eyes, around your eyes when you get old. Oh, why apples have formed, why you pinch your skin and you have wrinkles too. So it's actually all a competition of bending and stretching. All right, but if you're interested, I can tell you more about this. But okay, the bottom line is graphene is worse in a Saran wrap. You can. This is I already done this. This is single atomic version of that. So you can stretch it, and this is again you scale everything down by 10,000 times, 100,000 times. This is what you have. So another interesting thing is that it has strange thermal properties. Any of you have tried to put the Saran wrap in microwave and heat it? What happens? It shrinks. It shrink or it expand. It shrinks, right? So that's exactly. So that's another property of graphene. Is that it actually has so-called negative thermal expansion coefficient. Again, that's drawn from saying it contracts when heated up. So this is actually a contrast to most material, when you heat, they usually expand. So here's so this is basically heat-induced ripple formation. Here we show I don't know, you don't see it clearly. So single-layer graphene in the electron microscope. This is at roughly 200 Celsius, so roughly 400 Fahrenheit. And when you cool it down to room temperature, you can see the ripples start to form. And these are just induced because of this thermal contraction of graphene. Okay, so graphene is really just contracts when heated. It's like when you put Saran wrap on a Tupperware and heat it in the oven. Okay, so then you can form this nice periodic ripples. This is what we put a piece of graphene on an opening and then heat it up. So this you have found this very nice ripples, very periodic. So okay, so this is actually very interesting for the community of thin film mechanics, because actually it's a large community studying how thin film can fold or wrinkles, etc., etc. And graphene is actually the thinnest membrane you can ever have. But for me, as I like to study the electronic property. What does it mean? It actually means that we can exploit change the property of graphene by changing its shape. So this is because graphene not only is the thinnest material, thinnest membrane ever, it's also conducting membrane. And coupling the two is very strange. Usually you don't have that usually. And so that you wrinkle graphene, you try to arrange the atom little differently in the atomic scale, you can change the electrical property dramatically. For example, you can make it go in circles perhaps by just simply creating string in a certain configuration. So this is actually very nice effect. I'm not going to go through this. Lots of theoretical prediction. I'm not going to go through the details. But this is one thing, a very nice demonstration of one of these principles is this work from Berkeley, showing that a string-induced pseudomagnetic field greater than 300 Tesla in graphene nanobubbles, they form these highly strained graphene nanobubbles on platinum surface. And this is amazing because the highest steady magnetic field produced on Earth by humans is only about 45 Tesla and was produced in National High Magnetic Field Lab in Florida. So we want to get this 45 Tesla magnetic field, we have actually to send in proposals, we apply, and then we fly to Florida to use their magnet. But so electrons in this kind of strained graphene nanoribbons are experiencing something like 300 Teslas, which is amazing. And magnetic field can be used to make the electrons go around in circles. You can bend this trajectory. So that's this. So conceivably, this can lead to a new type of devices, for example, like lenses. Okay, so another interesting property of graphene is that it's transparent. And this is, so each graphene layer is transparent about 98% of light. Here's work from Masless's group. So here is a graphene over an opening. Here is air, so it's just transparent. And there's one layer of graphene. It's a little bit darker, and bilayer graphene is a little bit darker yet. And so this is interesting because most conductors are actually opaque. So think about metals. Metals have shiny, right, opaque. And think about plastic, which are electrical insulators, but they are clear. That's why transparent conductors are in so much demand, because you want transparent conductors to make solar cells, to make touch screen displays, and to, for example, and flat panel displays. So most common material for transparent conductor is actually so-called ITO, indium tin oxide. But indium's price, you can see that it changes from, it was actually about $100 per kilogram, and then it shoots up to $900 in 2005 or so. So since it dropped back down a little bit, but still it's way above its historical value. So graphene is actually a very promising alternative because it's very conductive and it's very transparent. And here's this, I don't know if I have time to show this. This is a demonstration from the from SKKU in Korea and in collaboration with Samsung. So already made a prototype of touchscreen using graphene. I don't know if I can. So I'm calibrating it. I guess you can't really see, but trust me, there's a layer of graphene on there. Okay, so all right, so I hope I have convinced you graphene is really the new wonder material. It's truly two-dimensional. It's only one atomic layer thick. It's hard to imagine how you can get thinner than that, maybe with protons, but those are not very stable. It's compatible with current silicon-based technology. So that's very nice. You don't have to redesign all your billion-dollar fabrication factories. It's stronger than steel, but softer than silk. It conducts heat very well, and therefore the heat removal will not be as much a problem. It also conducts electricity very well, which means you do not have to apply as much high voltage to this little transistors. It also carries a lot more current, so that the failure rate will be reduced. And it also is transparent like plastic, and it's also chemically inert and stable. And so it's also fascinating physics. So that's why graphene has tremendous promise as post-silicon electronics. It also is a very nice toy for physicists like me. So we can just scotch tape and do our experiments. Okay, so there's a lot of applications. Let me just go through a few. We already talked about electronic material to replace silicon, transparent electrodes. We can make atomic switches, chemical sensors, the capacitors for energy storage, flexible electronics, and also as a coating. And for example, anti-oxidation coating. This is work from Ruoff's group in Texas. So you take a U.S. penny and coat half of it with graphene, and the other half uncoated, and they put it to be oxidized. And you can see this half remains very shiny, and where the other half is completely tarnished. So this is just amazing. One single atomic layer is able to withstand all the oxidation. And so those who in the audience may say, okay, but you'll never get that with the rubbing technique, right? So those are good for laboratory research, but for widespread application, you will never get that. So of course, this is not true anymore. That's why graphene price plummeted. And so since then, so the researchers developed a lot of large-scale graphene synthesis technique, especially actually going back to the root. For example, remember people find that graphene is so annoying forming on surface of metals. Now they are revisiting that problem, phenomena. They are growing graphene on top of metals now. And so I'm going to just skip this. So there's of course, a lot of things still needs to be done before graphene can really replace silicon. But there is actually tremendous progress made. So this is I made up this Moore's law for graphene. Its mobility value, which measures how well electrons travel through graphene, is again also doubles roughly every 2 years. And the size of graphene she produced actually almost increased by a factor of 10 every year. So this is tremendous amount of progress in the past 5 or 6 years. And there are a lot of challenges to be overcome. For example, mobility and control. We need to control precisely the edge of a graphene, and we want to create band gap engineering. But each of this, there's a lot of smart people working on each of the problems. So I think there's really a lot of progress in this area. So let me just conclude by saying this is, you might ask what happened to graphene. I don't know really. It's a dangerous business to predict the future. But this is a science vision. I think it's one of the vision. It's actually a very nice vision. I certainly hope it will happen. So let me just, so they have, okay, so Samsung hopes to make this type of thing, this type of displays, a foldable, bendable electronics, and you can surf the web with graphene. And I certainly hope this will come true. And meanwhile, a lot of people are working on this. So let me just conclude by thanking all my collaborators. I have a large number of collaborators cornering Southern California market, and also thank all my students. Actually, my students are here. Most of them are here. I want to. So my students who work very hard and their hard work has made this presentation possible. And so my graduate students, undergraduate students, you already met David. And of course, funding sources, as everyone, which are supported by taxpayers like you. So thank you.
Do you have time for a few questions? Yeah. If graphene is massless, how can it be seen under a microscope?
Okay, so graphene is not massless, just only electrons in graphene behave as if they're massless.
Which means, so the electrons, they have mass.
They actually do have, if you take a single electron out, of course they have mass. But if you put in this kind of high cyclical lattice, they move so that the energy is proportional to momentum, which is mass times velocity. In that case, because from the Einstein theory of relativity, we call it it's massless, because it moves like a massless particle, for example, like light.
So it's wave and particle at the same time?
Exactly. Yeah.
Can it occupy two places at the same time?
Yes.
Oh, yes. Does it have any catalytic properties?
Oh, catalytic properties, interesting. I'm not a chemist, but any chemist here? I don't think so, actually. I do not think so. But it can be, what people find you can use, the same for nanotubes, is that it can be used as catalytic support. So, for example, all catalytic reactions, you actually want a large surface area to volume ratio. And graphene, all surface with no volume, right? And so that's why it's useful as a substrate for support for catalytic reactions.
Yes.
If graphene, the bucket of ring molecule, and the carbon nanotubes are synthesized into one huge network, what new physical or chemical properties would you expect those molecules to behave?
That's a good question. I don't know. If you make it, I'll measure it. That's of course, this is this is type of new physics we always look to do, right? Of course, the challenge is for the chemist in the audience, or any aspiring chemist, to make it. And usually, anytime you make a new structure, there's a lot of amazing properties that can happen. I really don't know. Maybe theorists in the audience can answer the question.
About graphene, you mentioned it's a new promising material. What other new materials would you expect to be promising in the future?
Another billion-dollar question, right? If I have crystal ball, I'm going to go out and buy the stock. For my personal opinion, of course, could be biased. I think graphene is actually the most promising material to replace our supplement silicon. So other materials people talk about, for example, carbon nanotubes, various kind of nanowires, even organic molecules. But I think those type of materials, the problem is that they are not two-dimensional, they are not planar. So they are kind of either one-dimensional or zero-dimensional, like a ball, a little point objects. And it's difficult to put them where you want them. So it's difficult to control the placement. So that's why graphene is nice. It's two-dimensional sheet. You just cut it where you want them. So in my opinion, graphene is probably the most promising material. But sometimes you never know. So there could be some other material come out to replace graphene. But I will welcome that too.
Yeah, one of your slides mentioned the application, and you had a bullet point that said biochemical application. Wondering if you could tell a little bit about that and what's going to work.
Oh, so this is basically just to use, you mean the bio and mechanical sensors, bio and chemical sensors. So you just take graphene, the same works with nanotubes, and you, for example, put some chemical groups, and then you can use that to detect target molecules. So the chemical group, so they will, when they react with the molecule, they will cause some changes in graphene, for example, cause it to become less conductive or more conductive, then you can detect it. Another way is actually another way I'm working on with my collaborator, is that you can also make a mechanical resonator out of it, and the frequency of the resonator depends on the mass. So when the target molecule was attached to this reactant, the mass will change, and you can actually detect that too. So there's actually, you can possibly make, for example, on-chip mass spectrometer with, arrays of graphene. These are the possibilities, which I think there's actually a lot can be done.
So they're both electrical and mechanical?
Yes, exactly.
Okay, last question. So is graphene actually used in any product today, or is it still in the research phase?
It's still in the research phase. Of course, it's always difficult to predict the future. I would say the most promising application right now looks like the transparent electrode for touch screens. I think those are actually, you can probably see some product on the market. To really replace silicon, actually, it's a lot of work has to be done in that area. Right now, at least the semiconductor industry are looking at about, say, 15 to 20 years out. For example, that's, it's, we have 15 to 20 years to prove that it's really usable.
Okay, let's thank Professor Lau.